So hello students and welcome to Mehta PG College online study portal, and today this is lecture 8th recorded for B.Sc first year physics, paper 2nd electromagnetism, and for English medium students. And today in this video we will talk about Gauss's divergence theorem, or simply known as the divergence theorem. Recently with our lectures like the lecture 7th or lecture 6th, which were pretty much important for us, if you consider lecture 4th and 5th, then you will come to know a vector dimension to be calculated, which is the divergence of vector field, which was discussed in lecture 3rd, and the dimension, which is the curl of vector field, was discussed in lecture 4th or 5th. So this is the time when we are supposed to enhance our knowledge. So let's begin with this particular topic, saying Gauss's divergence theorem or the divergence theorem. Let us consider what the thing happened here. This is a relation. Yes, this is even a theorem, also a relation, and sometimes you can term it as an identity. You remember the identities we discussed earlier in the lecture 7th of our series. So let's proceed here. What is the Gauss's divergence theorem says? It says, if you consider a volume, any certain kind of volume, you can say it could be spherical, it could be cuboid, it could be a cubic shape as in volume case. So let's proceed here. Let's say there is a volume, it is some unidentified volume. You can see this is a volume. Every time when we are talking about divergence, that relates with a far more discussed concept, which was the vector flux. So divergence relates us to the vector flux concept. So let's see, this is a volume, and for this we have calculated divergence, saying for any vector A, in a sense, then what does the divergence approaches to? This approaches to the surface integration of vector flux. Remember, closed surface integration of the vector flux per unit what? Per unit volume. Yes, it has been discussed for the per unit volume case. This says that the limit dV approaches 0 and here is the limit dV approaches 0. This is again closed. 1 over dV and the surface integration of the flux A dot dA vector. So this is what been discussed earlier. So this is the time for us now to give a relation between this surface integration to the particular volume integration. So what is the particular volume, you say? Let's say this is a volume element we have. Consider we got a surface element here. This is the cross section area from where the flux will be passing here. Let's see, this is the flux for vector A. You say, I simply write it as phi A, because flux is which kind of quantity? It is a scalar quantity. Okay, it either have direction, no, it has only magnitude but not the direction. In case of this volume, this whole volume must be consist of some infinitesimal volume elements, you say. This is the whole volume element. This is the whole volume, which is consists of infinitesimal number of volume elements. Okay, this is the whole volume, which is consists of infinitesimal number of volume elements. As in this video we have a focus here for this particular surface, we will talk about this face only because it is subjected to us. So how does it relates to us in the Gauss's divergence theorem? Gauss's divergence theorem or the divergence theorem will give you a relation between the divergence of a field over a volume to the flux integration to the surface integration of the flux to the volume integration of divergence. So it will be a relation here. So this is what the example we are discussing here. Let's consider this is the surface area having the phase direction say ds vector, and the vector field here is a vector as discussed. Let me say this is the vector representing, this is the representation which is representing vector a, let's say, and this is the whole surface area over here, which has a direction, you say in the direction the particular direction which is perpendicular to the surface, say in this same direction, it say the direction has ds, or in short dA. Yes, the surface has its direction here, the direction which is dA. So what does Gauss's theorem states? Let's talking about its statement. How will you know that this is Gauss's divergence theorem or it is? So what does Gauss's divergence theorem states? It says the surface integral of a vector field, here let me say the statement is that the surface integral of a vector field over a volume, because we are discussing about volume here, but this volume is specified in sense of this closed surface over a closed surface is equal to the over a closed surface is equal to the volume integral of divergence of that particular vector field, of divergence of that vector field. Okay, so this is the statement, and as we have discussed, we will prove it step by step that this will approaches to the statement there. So this is the statement. You can take a screenshot for your reference, and then I will explain something more about it. Okay, so you got a screenshot of this statement. Now we are supposed to prove this statement mathematically, so we will prove this. So let's start with this mathematical approach. So before starting, we need a workplace over the whiteboard. So let me clear this off, the existence. I think we can use this space here. So let's begin with, let's say this volume element, this is a particular volume element, consists of literal infinitesimal volume elements. That sounds pretty much crazy for you. This surface element must have, this particular surface element, this is which is dA, the surface element dA must have the surface element must have infinitesimal number of volume elements. Infinitesimal number of volume elements, say if we consider the vector here, then the vector will again have all the components associated with all those infinitesimal number of volume elements. Okay. So if you got this infinitesimal number of volume elements in the form of parallelopipes. Parallelopipes is some sort of volume element saying every side is parallel to each other. There are 6 faces and about 1, 2, 3, 4, 4, 4, 4, 8 and then 4, 12. About 12 sides. All those sides are equidistant to each other, means you can say that all the alternate sides which are parallel to each other. So that's why it is called a parallelopiped. So parallelopipe is simply represented as this. So this is how a parallelopipe appears to you. So say that this particular surface element, this is the only surface element which have all the answers to our questions. Let me color this again. Okay. So this is the surface area which have all the confusions here, which is the reason that why we are discussing and why we need the Gauss's divergence theorem. So this is the whole region which has all the answers to our question. What kind of answers we have? This surface element is certainly have some sort of width, you say, maybe the width about this. Every time when you consider a surface, it must consist of little volume elements which gives it a shape over there. Okay, this always gives it a shape. So for this shape there are infinitesimal number of volume elements, says that d this. So let me say the surface has all the surface elements in the form of parallelopipe, say dAI. Let's say this is the face approaching to you, because every surface element is made up of all the volume elements. Then all the volume elements must have a surface element like this. This is the green face, and the green face here, this has a large number of this kind of structures. Okay, and the appearing structure to us, this only the green portion here. So the number of these green portions may be represented for this. The ith particle here is represented as dAI. For sure, that's yes, that's dAI, and the vector which is representing this infinitesimal volume element maybe says AI. So this is the vector here AI, and this is the particular surface element. So the whole surface element may be considered as consisting of a large number of these elements. So how it can be written as? It can be written saying as the mathematically you can say the statement here. Mathematically you can say this as like that: closed surface integration of A vector dot dA vector is equal to summation of closed surface integration again, but for what? All those infinitesimal element AI dot dAI. You see what is it? Yes, that's amazing, and that's pretty much cool. The summation is to be subtended over I. Okay, This is the summation over I. So how the whole thing we have discussed here is written mathematically in this sense. So this is the mathematical expression. Let me proceed further with this expression. Let's say what we find out. Every time the flux emerging out of a volume element is represented as the divergence. Okay, every time it is represented as divergence. Surely from this equation, you see this. Okay, we consider this equation here. Let's say this is equation 1 and this may be equation 2. Okay, now see from equation 1, what will happen? Let's see what happened. From equation 1, what we have integration of a surface A dot dA vector, also A vector is also considered, is equal to del dot A vector or the divergence of A vector multiplied with dV. Yes, this is from equation 1. But what if this is considered for the ith element? Then we will simply say this is AI dot dAI is equals to del AI dVi. This is for the ith element. Say this is equation 3. Now we have two equations here for our confusion, increasing our confusion, which is the equation 2 and equation 3. So from equation 2 and 3, what will it happen? We can simply replace this term by this one. If this is the summation means that you do not need you need not to mention all the infinitesimal elements. You can simply write a single element over there, and that will be for all. Okay, so let's represent it. This is dVi is the volume of ith volume element. So now this is also can be written as from equation 2, from equation 2 and 3. So what do we get from equation 3? We just get integration over closed surface A dot dA vector is equal to summation again over I del dot AI vector dVi. Okay, this is for the infinitesimal elements. If the elements has an infinitesimal number, then this summation can be replaced by a integration symbol. Simply this summation can be replaced with integration of all those elements. This can be replaced. So when we replace this integration, this summation, this is the summation symbol which has been replaced by integration symbol. This can be replaced with integration A dot dA vector will equal to integration over what? Integration over volume, because there are infinitesimal number of volume elements. Okay, integration over volume del dot A vector dV. Every time surface has a direction but volume has no direction. Okay, dV should not be mentioned vector here, because everywhere we discussed the volume element, then we hadn't discussed the vector or the scalar nature of volume, because volume has no direction for particular. Yes, certainly the faces for volume certainly has some direction. So you can say if this is a cylindrical tube, then every time cross section area has a direction, and you can specify. But for a volume element, if you have a surface area over surface, then it will form a volume, and every time when you are talking about a volume element, then you cannot justify a single direction there. So when you cannot justify a single direction, as that in case of electricity, the thing happens what? The thing happens is that the quantity should be considered as a scalar quantity but not the vector quantity. Okay, so not last but least, we got our mathematical approach here. So this is what we are supposed to end up with. we end up with the same statement we have written over here. This is the statement. We have proved its mathematical form. This is the mathematical form for the statement over there. The statement which said that the surface integral of a vector field over a closed surface is equal to the volume integral of divergence of that vector field. So, this is what the surface integration of a vector field is equal to the volume integration of that vector field, volume integration of divergence of that vector field. So, this is what we are supposed to prove. I hope that you are known of how to deal with this kind of questions. So, that is all for this lecture, and we will proceed further with its divergence form, and we will drive out how this formula will be justified. So, according to our tradition, let me clear this off and then we will proceed further. I hope that you have taken your screenshot yet. Take it by step. We will go for far, but not in hurry. We will go easy and we will do it pretty much easier. It is the easiest sense I can give you a brief explanation of these kind of topics, because these kind of topics are not only important for your examination for B.Sc first year, but these topics are also important according to the examination, like as the entrance examination for various universities, or if you want to become a scientist in such kind of the entrance for BARC, the GATE exam, in such kind of exams, then you will need a brief introduction to these kind of questions. Okay. So, let me clear this off and then we will proceed further with its differential form. Okay, so we have cleared our board here, so and we are ready for a next topic. So, let us start with the differential form of Gauss's law, but from this we are supposed to derive Gauss's law. You remember the Gauss's law? Not the Gauss divergence law, but the Gauss's law. The Gauss's law which say that the flux emerging out of a surface is equal to the flux emerging out of a surface is equal to the ratio of charge per unit surface, per unit volume. Okay, so this kind of explanation which has been given by the Gauss's divergence theorem, which says that the flux is equal to Q over epsilon, the permittivity of the medium. We will discuss it shortly. So, the topic is derivation of Gauss's law from inverse square law. Okay, so we will use the inverse square law here and then we will define the Gauss's law. Okay, students, so we are back with the topic that where we left our video, the derivation of Gauss's law from inverse square law. So, let us start with the topic, but first of all I would like you to remind the inverse square law. If you remember, what is the inverse square law? Because in physics there are certain quantities which is explained like as the force, like as the electric field, and these kind of quantities which are being explained, which are inverse, which follows inverse square law, because these quantities are inversely proportional to the square of the distance, because every time the distance increases, these quantity feels an exponential decay or in such type of decay in their magnitude. Okay, that should not be discussed right now. We will go through the topic and then we will discuss all these step by step. Okay, so let's start. Consider every time the Gauss's law, when you consider, we need a surface over here. The surface doesn't need to be a perfect surface. It could be any kind of surface. It could be a tattered surface and some sort of like the separated or this should not be combined pretty much easier. So let's start. Let's say this is a surface area here. Okay, this is the surface. We got this. Okay, very well. Then every time we need an observation point. Sure, we need an observation point. Very well. Also, every time when we're talking about observation point, but we are talking about the inverse square law, then we need electric field over there. With electric field, we can perform all these actions. In sense of vector, we got a field saying E vector, the electric field vector, because every time when we need to explain the Gauss's divergence law and the Gauss's law, we need a vector field. So electric field is in electric field because electric field has its direction in this direction, particular this direction. Let's say the solid angle. Okay, this is the time we need a solid angle, but first of all we need a surface to represent the Gauss's law. So this is the surface. Joining these points. Okay, we have joined all these points. Yes, say let's say the point here which it strikes. This is a surface. This is a surface area. We have discussed in the recent topic that for this vector field we need to calculate the flux, and every time when we are talking about flux, flux is the amount of a vector quantity which has been passing from a particular surface area. So this is it. The point P is on the surface at where the electric field line is emerging out, and the displacement vector you say for this surface area, the displacement vector for this surface area is R. Yes, this is the distance. As this surface is a little bit tilt over there, it has a tilt. So the perpendicular direction for this surface, let's say this has this particular direction, ds. ds is the direction of surface. Yes, it is represented with a vector symbol because it is a vector quantity for sure. Yes, for sure it is a vector quantity. Let's say here is a positive charge plus q at point O, just because of which the whole thing is happening over here. This is the direction of electric field, because every time when you consider a positive charge, then the direction of electric field is always be emerging out of that. Every time the direction of electric field will be some sort of like emerging out of that. This is for the positive charge. It is that what you have studied in your 12th, but I should repeat here for the conceptual knowledge, because every time when there is a positive center, then the direction of electric field will be outward for the positive center, because it doesn't like anything to be on itself, because it is selfless, it made selfless. But every time when you consider a negative center over there, then the direction of electric field will be inward. It is some sort of electric field lines entering in something, entering in the negative center. This is not something, but this is the negative center you say. So this is what happened in case of when there is a positive center and in case when there is a negative center. But we consider a positive center so that there will be no complication like how to deminimize the minus sign or how to diminish that. So that's why we consider only the positive charge here. This is the test charge Q. We do not need it because this is only for explanation and we need a workplace. So that's why I am clearing this off. Let's proceed further. First of all, we have a very considerable example which is following the inverse square law, which is the electric field intensity, or simply in terms you can say electric field. Okay, let's find out the electric field for this arrangement. So what the value of electric field will be for this point P. Electric field for point P, what it will be? Electric field again is a vector quantity, is equal to 1/4 pi epsilon for medium and epsilon naught for vacuum. So let's see, we need epsilon over here because the surface must have a medium. Surface should not be considered in vacuum because then the surface will have no meaning over there. and the flux will change only when there is a medium. If there is no medium, then flux certainly do not change. And so that's all what happens. So we consider a medium over here, that's why epsilon is taken instead of epsilon naught. The charge is again q here, and the displacement vector is r square, and the direction is r cap for sure. This is a pretty much good example or a very vast example of quantity which was following the inverse square law. This is it. This is the quantity. We will use this value to find out the Gauss's law. The Gauss's law, remember, we have discussed. Let me write in some sort of bracket here. Phi is equal to q over epsilon. So this is what you can say is the RTP, or in sense it is something to required to prove. So let's prove it. Okay, so what the things we have here? We have electric field intensity, which we are talking, and Q is the test charge which has been taken here, which is the charge taken in here, and electric field at this surface, this particular surface, for which the electric field intensity should be considered, and ds vector is the direction normal to the surface, and r cap gives you the direction of position vector. R cap gives you the direction of position vector. This is the position vector, and r cap gives you the direction in certainly in the same direction for where the surface is increasing. So let's proceed further. So what will be the value of flux emerging out of the surface ds? Say the value of flux. Thus, the flux emerging out of the surface ds. Yes, we have the surface ds over here. So what will be the value of flux? The value of flux phi d phi will be equals to E dot ds. Let's say this is equation 1 and this is equation 2. So these two are the equations. This is the value of flux emerging out of the surface ds for electric field E, because the vector here is E vector. So okay, again we use the value of d phi for the electric field E, and then say what we will end up here. Okay, using equation 1. Using equation 1, d phi will become 1 over 4 pi epsilon, yes, q over r square r cap dot ds vector. There is something comes out which is not supposed to be come out, which is the r cap dot ds. Now we have to solve this quantity first, and then we can talk about d phi over there. So let's solve r cap dot ds. Since r cap and ds, all these follows certainly the same direction, ds must have some angle inclined here. You see, E vector also represents the direction of r vector. You can say yes, this also represents the direction of r cap. That doesn't matter over there. Okay, this must have an angle between them. These two quantities, the r cap, which is a unit vector, normal unit vector following the direction of displacement vector, and ds is the vector representing the direction of surface. They certainly must have an angle between them. Say the angle is theta, which is represented here. Let's say the angle here is theta. So what will be the value of r cap dot ds? Now r cap dot ds vector will become magnitude of vector r ds. Every time when you are talking about dot product, it will approach to cos theta. ds cos of theta. Since it is a unit vector, so the magnitude of unit vector will always approach to 1 only. This is a unit vector, so its magnitude will approach to 1. So what it will become? R cap dot ds vector will become only the ds cos of theta. We will use this result over there, but we have to specify something here. Okay, let's come to the observation point. From the observation point, when you are observing the surface, then certainly you will follow our lecture 5. Yes, you will follow our lecture 5th. Our lecture 5th, which was for the concept of solid angle. So what is a solid angle? Let's specify what is a solid angle. This is the angle which is formed in 3D, the observation angle, how you can see a quantity or how you can see a surface is termed as the solid angle. So this is the solid angle over here represented by d omega. Yes, it is represented by d omega. So what will be the value of d omega? If you remember our last sections, let first say what will be the value of d phi. The value of d phi will be equals to 1 over 4 pi epsilon q over r square ds cos of theta. Let's say this is equation 3. Okay, so what will be the value of solid angle? So the solid angle which is d omega is equals to ds cos of theta over r square. If you remember our previous section, in our previous section we have discussed the value of d omega, how it value has been drawn here. How will you end up having this value? This is the d omega which is equals to ds cos of theta over r square. Okay, let's proceed with this value and use this value in equation 3. What it will become? So equation 3 becomes, by now equation 3 becomes d omega, sorry, not d omega but d phi is equals to 1 upon 4 pi epsilon q into d omega. Yes, this will be the value of equation 3 will reduce to d phi is equal to this value. Okay, we have a new value here. Let's say this is equation 4. Yes, this is equation 4. So this is the term here when we find out the value of d phi. In this case, if we approach the value of phi here, the total flux emerging out of the surface, this is d phi, this is the flux element which is emerging out of the surface, but we do not need the flux element only, we will talk about the whole flux emerging out of the surface. So that's why we will integrate these small elements, because this is the infinitesimal small element here. So let's integrate equation 4, saying the total flux emerging out of the surface, emerging out of the surface will be equals to phi equals to integration of d phi over that particular closed surface. Yes, and this is again equals to the closed integration of equation 4, 1 over 4 pi epsilon q d omega. And if you remember that the value of d omega for a closed surface integration will approaches to 4 pi. Do you remember? If you don't, then go and check out the lecture 5th, which is all about the concept of solid angle. So let's say what does this equation will become? Okay, what does it will become? It will become this is 4 pi epsilon. So phi will be equals to 1 over q is also a constant here, 4 pi epsilon integration over closed surface for d omega, which is the solid angle, and the value of solid angle is equals to, what does this value will approach to? This value will approach to 4 pi. Yes, the value of solid angle which approaches to 4 pi. Yes, you can see all the objects in your 3D space with an angle which is equals to 4 pi, which is called as the solid angle. This is the concept of solid angle. You can check it out for lecture 5th, which has been uploaded recently. Go and watch it. If you don't, then you can understand this topic pretty much well than what you are understanding right now. I am connecting all these topics with each other so that you will not got confusions over there. Let's continue. So the value of phi will be equals to, what does the value of phi will equals to? Q over 4 pi epsilon multiplied by 4 pi. Yes. We will cancel out 4 pi with 4 pi. So what will have? What will we have? We have phi is equals to q over epsilon, and this is the Gauss's law. Yes, this is the Gauss's law, which we are supposed to come out to be. This is the mathematical statement of Gauss's law. How will you state Gauss's law literally? How will you write all this? So you can take a screenshot for your reference. Let me be aside, and then we will clear this off and write the literal statement of Gauss's law. Okay. Let's say give it an equation number. Say this is equation 5. 5 is not written so much handsome here, not so much good. So how will you define Gauss's law in literal? The flux emerging out or entering in a surface is 1 over epsilon times of the total charge enclosed by the surface. So this is how you define Gauss's law literally. Okay, this is the definition of Gauss's law, or simply mathematically you can say phi is equal to 1 over epsilon of total charge q. Okay, so this is the proof. This is what you are supposed to derive from the Gauss's law in derivation form or the differential form of Gauss's law. Okay, you can take a screenshot, then I will clear this off and we will proceed further. We will discuss the Gauss's law in differential form by now, and we will relate all the values, which is the divergence theorem you see. Okay, so according to our tradition, let's clear this off. Okay, so we are ready for a new topic here, and the new topic which is Gauss's law in differential form. Yes, we will discuss Gauss's law in its differential form, and after then we will discuss the Stokes theorem, and with all these examples we will end up having chapter first completed. Then we will proceed for the second chapter, which is the second half of your first unit for electromagnetism. Far more within this month we will complete your first unit for electromagnetism. Then there will remain only 3 units, and we will do them step by step. Okay. So let me write down the topic here. Sorry, not write down but write up the topic here, which is the Gauss's law in differential form. Yes. Gauss's law in differential form. Okay. So what is Gauss's law and why do we need its differential form? You remember the Gauss's law, which says the flux emerging out or entering in. I am repeating this definition about 7th time within this lecture. Okay, sorry, I am repeating this definition again and again, but it is what the necessity you say. We need the differential form for Gauss's law. You remember the Gauss's law, which says the flux, the total amount of flux which is emerging out or entering in within a surface area will equals to the 1 over epsilon time, which is the permittivity of that particular medium, 1 over epsilon time of what? Of total charge enclosed by the area. Then why do we need its differential form? What is the uses of differential form of Gauss's law? The uses of differential form of Gauss's law will approach you to the 4 main equations of electrodynamics, which are the Maxwell's equations. Yes, the Maxwell's equation. This will approach you some certain equations saying the Maxwell equation. This formula will approach you one of the Maxwell equation. Yes, we will approach this Maxwell equation. Maxwell equations are valid not only for electrodynamics but for hydrodynamics also. Yes, these are valid for hydrodynamics. There is one more term here. Which is the hydrodynamics. Okay, you do not have to worry, because we will not discuss hydrodynamics here. We are subjected to read only the electromagnetism, or in the sense it is the ED or the electrodynamics of your subject. Well, let's proceed. We do not need it here because it may distract some of our students. Yes, it may distract. Yes, distract. It may distract some of our students. So let's begin with this topic, saying the differential form of Gauss's law. First of all, if you remember the permittivity here, the statement of Gauss's law which says that the flux phi is equals to 1 over epsilon time of total charge enclosed by the surface. So what is epsilon? Epsilon is the permittivity of medium. Yes, epsilon is the permittivity of medium. Yes, sir. This is the permittivity of medium. So what if we discuss permittivity of vacuum? How will we symbolize this 1 over epsilon with 1 over epsilon naught? So when epsilon is equal to epsilon naught, this is for vacuum. For vacuum, epsilon is equal to epsilon naught, which is equals to 1 over 36 pi. Sorry, not omega, but 1 over 36 pi into 10 to the power minus 9 Coulomb square Newton meter square. Remember this unit? This is the unit for epsilon naught, or simply you can say this is it. Farad per meter square. farad per meter. This should not be meter square, it should be meter here. Let me check it out. Sorry, this is meter square. Okay. So farad per meter is the unit of epsilon naught, the permittivity of vacuum. Well, this is not necessary for us. Why I am talking all this? This is just for explanation. So let's talk about the Gauss's law. Saying that if a element, the whole surface element, say there is the whole surface element having charges q1, q2, q3 having charges q1, q2, q3 and so on up to maybe it's up to qn, enclosed by an imaginary surface enclosed by an imaginary surface. Say this surface is S. Yes, this surface is symbolized as S. So the total charge enclosed if you symbolize the total charge as Q, then it will become Q1, Q2 plus Q3 and plus so on, maybe up to Qn. This will be the summation of all these charges. So what, when if you summarize all these charges together, what will you end up? You will end up having a flux. Yes, these all charges are summarized, and so the flux will be, so the flux which is represented as phi is equals to integration over that particular closed surface, because flux is always represented by a surface, E vector dot dA vector. Yes, this will equals to this, which you say equation 1. Yes, this is equation 1. Phi is equal to integration over closed surface E vector dot dA vector. But according to Gauss's law, according to Gauss's law, your phi is equal to, which is equals to the closed surface integration of E dot dA vector, phi is equal to this, and is equals to the whole Q over epsilon, or yes, this will equals to this. This you say equation 2 here. Also remember, do you remember the charge density? What does the charge density equals to? Charge density is equals to the total charge enclosed by a volume. Yes. Total charge enclosed by a volume will represent charge density. Remember? Let's say charge density is equals to charge over volume. Yes, this is equals to charge over volume. So charge on density, if you say rho is the charge density, what does rho represents? Rho represents the volume charge density, which is equals to